which when I don't know, I still don't know myself because I have to fix it. We'll switch a little bit into revision mode. I will share a bunch of questions with you for practice, okay? But even beyond that, I think we can do a few exercises, so to say, tomorrow, okay?
Will someone fit there?
So for now, however, today let us focus on a very important factor that arises when you're looking at biomolecular systems in general, biological systems in general, and it is sometimes underappreciated. You don't, these very tiny entities, these tiny factors, they play a tremendous role in how biology can be controlled. We all know by now that biology occurs in water, right? Please quieten down, kindly, please, okay? So thanks to the TAs, we have some movies made from computer simulations. Is this visible? So this is bulk water, box of bulk water, okay, simulated at standard temperature and pressure, right? And those little yellow broken lines that you see, those are hydrogen bonds, okay? Now you might ask what happens to the hydrogen bonds at the edges. Okay, if you don't stop that, I'm going to throw you out of the class. I'll pretend you're in standard 10 and I'll throw you out, right? Please don't make me do that. So those little yellow dots, we can make it thinner or thicker depending on our choice of representation. But those are hydrogen bonds done, this is a simulation done in my group by my students. In computer simulations, we use a trick called boundary conditions, periodic boundary conditions, such that, this bulk of water is essentially very close to, boundaryless, infinite water, okay? Now, when you look at this, are there few things that come to your mind? If I were to somehow, focus on just 2 or a few pairs, a small group of water molecules, say 5 or 8 water molecules, what would you expect? The hydrogen bonds are very dynamic, you notice that, right? They are making and breaking all the time, right? So there will be some kind of statistics associated with these hydrogen bonds. There will be a time, okay? Of course, if I take one particular time window, let's say 10 times more than the average lifetime, you will see a lot of different kinds of lifetimes, right? So there's an average lifetime, and also why are these hydrogen bonds formed in the first place? Because, it's energetically favorable, okay? There's a stability that hydrogen bonds bring about, okay? There's also, why does it break? It makes because of energy. Why does it break? Entropy, right? So, there's entropy gain if your hydrogen bonds are able to be configured, okay? So, we will, again, this being such a basic class, we will be limited to, very basic elementary discussions. But I hope this will kind of encourage you to look forward. There are very, accurate ways of calculating the energetic and enthalpy components. We'll do a few problems today. Now, if I go from bulk water down to, we have 2 more movies. We have also simulated, what looks like a protein. You can see, you can recognize the secondary structures. There are 3 beta strands. There are some other things as well. Okay, if I can tell you, if you look at the lifetimes and the energetics of this kind of hydrogen bond, we have looked at waters very close, within a few, less than a nanometer away, I think 0.4 nanometers. Half a nanometer away from the protein surface, those are the waters. They are usually a little bit more sluggish, okay? And so I'll play it again. At the end of the day, it's very dynamic. Okay, so there is always an energy entropy balance going on. Okay, energetically it wants to make these hydrogen bonds, but entropy is telling me if you leave, you'll be happier. At the end of the day, what matters is the free energy. Alright? Let us look at one more movie, and I really thank you guys for making these. This is a different representation, but again, this is too fast. We'll have to slow it down a little bit. But then this is our choice, you know. Usually in simulations we use discrete time steps of femtoseconds. I don't know what the saving frequency is here, but we can slow it down a little bit. Say that? We'll do that, and I'll share the movies, don't worry. We'll redo the movies, we can just adjust the saving frequency and these things. These are discrete time molecular dynamics simulations. So again, but the central message is it's very dynamic. Okay, here the hydrogen bond representation is red, right? So you know, if I just freeze the frame, you can see, you know, some of the hydrogen bonds will show up. Okay, thank you, but maybe we can adjust the frames a little bit and share it. Okay, now let's actually look at, you know, let's play with some numbers. It will not be very difficult. So hydrogen bonding in water, or rather hydrogen bonding of biomolecules in water. I'll specifically talk of proteins, but roughly the same principles will apply if you know, take some double-stranded DNA or RNA or whatever you like on a complex, RNA protein complex. Okay, you can even take a ribosome, whatever it is, you can put it in water. The principles are similar. It is just that the balance is shifted one way or the other. Okay. So, but today we'll focus on the protein perspective. Okay. So we have covered this, that you know, water has very special properties, and it arises due to, you know, the net dipole moment, the lone pair, so on and so forth, and that gives rise, that is very commensurate with this kind of a structure, right? You have this, what structure is this called? Tetrahedral. Okay, there are 4 faces. So each water molecule can hydrogen bond with how many? 4 at a given point of time, and this is the most optimal condition. But obviously this will be changed. So just notice, you know, I'm going to call this oxygen A as donor, and the oxygen, no, sorry, this is the donor, this is the acceptor. So what is the donor acceptor distance you are noticing here? Keep it in mind, 2.82-ish angstrom, right? This will change a little bit. Now, again, low battery, cancel. Okay. So we have gone through all this, right? What if we want to, you know, immerse a solute? So size is roughly the size of water molecules, just a little bit here and there. We might disturb the hydrogen bonds a little bit, but if we have a much bigger solute, okay, we have to pay a greater, you know, there's a greater cost. I'll take an example today. It may not be just a cost, it may be a favorability as well. So let's see. But the free energy change, for now, you know, I've written cost, but I'll change this to in a general form. Free energy change is proportional to surface tension and the size. Rather the area. We have assumed this is spherical, but the area. Remember that a biomolecule is not obligated to be a perfect sphere. It is the problem with biomolecules. Well, that gives us good problems to deal with. They are very misshapen. Can take pretty much any form. You cannot assign a beautiful fixed geometric shape to a biomolecule in general. Okay? They will never be, you can at best call them spheroids. They are never going to be a perfect sphere. The heterogeneity that you have, you know, in their sequence, in the 20 amino acids, in the conditions. I know that somebody told me that in your school you are taught that, you know, but you know, there's more subtle things. Again, the energy entropy interplay. This is assuming it's a perfect oil drop. A protein is not a perfect oil form. Okay. Okay, so we had already discussed this, and we have, so water helps protein achieve functional flexibility. I think, looking at those movies, it will be slightly more convinced. Okay, let us get to a problem. I shared it last time, alright. So, pull your calculators up, obviously. So, here we have a situation where, so there's a spectroscopic study, and I shared a reference last class. I'm not showing the reference here today. So a study showed that the breakage of a single H bond within pure water, okay, no solute, at 300 Kelvin is commensurate with an enthalpy increase. So if I break one water, if I break one hydrogen bond from that network, I slip one. Okay, how am I going to slip one? You have to be a really cool experimentalist to do that. You have to be technically trained in order to make sure that I'm removing one. You do certain tricks, but at the end of the day, there's an enthalpy increase of 1.9 kcal per mole and an entropy increase of 2.4 kb, right? How many of you remember that the unit of kb is the same as the unit of entropy? Unit of kb is the same as the unit of entropy. Why? Energy per temperature. Similarly, if I am talking of entropy per mole, I should go to R. Okay? So please remember these. If you, what I just said, make a mental note, make a pen note, it's up to you. These are things which will help you in your understanding and also in your exams. Okay? So, here we have a situation where I'm going to try to estimate what is the free energy cost of breaking a single H bond at room temperature within bulk water. Okay? So I'm going to, of course, write delta G equal to delta H minus T delta S. So delta H is increase. So what sign should I give to delta H? It's going up, right? So I will put plus 1.9 minus, so I'm going to put T as 300. What is my delta S going to be? Equivalent of, so is my delta S going to be plus or minus? It is also going to be plus. Plus some quantity. So I can put plus 2.4 into, if I have to do KB, I can essentially do R. I have put R. It's in kilocalories, you are right. So I should divide by 10 to the power 3, right? Is that okay now? R is? We can, so I must divide by 4.1. Is it okay? Now? 4.2, use 4.2 if you wish. I can do another approximation, right? I know my RT. This entire some 24 or so lectures plus the tutorials we have been hammering on you. RT is 0.58 kcal per mole, right? So I can smartly use that approximation as well. So I can simply write this as minus something like 0.58 in kcal per mole. Is that okay or not?
Divided by any, right? Because 0.6 kcal per mole is only where you have any.
I've used an R there. We used an R there.
Because it is asking for free energy cost of breaking one single one.
Right. So you could look at it that way. I see your point. But fair enough. Okay. I'm saying I'm breaking only one. So I should only talk of, joules or kilojoules. Fine, you can do that. But generally speaking, even in these cases, when you're doing biophysics, biochemistry, chemistry, physicists will use electron volts and other kinds of units. But generally we talk of, if I'm breaking one, but let's say I'm doing it for an entire ensemble or something, we typically use kcal. But if you do it in absolute joules, that is fine. Is that clear now? So how much is it? Or more importantly, is this number positive or negative? Positive, right? How much is it? Yeah, 1.8. This is approximately, correct me if I'm wrong, I'm getting 0.53-ish kcal per mole. Right? So I'm going to put a plus very boldly. Something like this. Just be consistent. Okay? So what does this mean? From these considerations, it looks like, if I have the entire thing in bulk and I'm just clipping one hydrogen bond, it is not very feasible. My entropy is going up, but my enthalpy is not, I'm not being able to compensate for the enthalpy with my entropy increase. Okay? Yes.
You're multiplying by R, but you're not dividing by R. Essentially, you're adding one extra R term.
Am I? So we did 2.4. We did 300. Okay, so instead of KB, I'm doing equivalent. Say I used equivalent.
No, but there is R.
Look, delta S is 2.4 kb, right? If I want to say kcal per mole per Kelvin or energy per mole per Kelvin, I can simply say 2.4 R, isn't it? Then I am multiplying with T.
Right, but here 1.9 is kcal per mole, but for that to also go per Kelvin, you have to do something because R introduces a per Kelvin term.
No, but I am multiplying by 300, I am multiplying by temperature.
That is separate, but
No.
what I am saying is that kb that is there.
Huh?
kb
Look at the units of kb. It's energy per temperature. Temperature goes on. Please realize that.
That's fine, but kb becomes.
Acha, how many of you have not think that there's a problem with this calculation? The second level. What is the TA opinion? Huh? It is fine. So, Abhinav, let's discuss this. Please take this opportunity to clarify things. At least your R and KB, regardless of whether they are in per mole or not, they are per unit temperature. So when you multiply by T, it goes away, you end up with energy, either energy or energy per mole. That is going on. So when I multiply with, you're saying that 2.4 R or whatever. You can work it out, Okay? But I'm simply going to use this information, the second one that I already know, my 0.58 value, okay? And this gives me a positive delta G. So if I ask, is this process favorable at this temperature given this? Answer is no. But if I ask this question, what is the temperature beyond which this process should be favorable? How will I find that? Exactly. When my entropy and enthalpy exactly cancel out, below that temperature regime, entropy is not favorable. Above the temperature regime, your entropy should be favorable. So, okay. So part C, let's call this A, B, C. This is A. In C, if I have delta G equal to 0, implying delta H, I'm just simply going to call it T critical or whatever. Delta S, okay? So T critical should be delta H by delta S. What I can simply do is I can, scale this, right? So can you work this out? I can simply take this part here as well. What I have done is I have done 1.9 by 2.4 into 0.58 into I can do, so T critical by T should be I can just so I can simply do it is going to balance out. Did this happen? I can simply do T by you have to multiply or divide by 3 and check this, right? How much does it come down to? It exceeds 400 Kelvin, right? 409-ish? Huh? 395. 395-ish? So it is significantly above the room temperature. This is simple unitary methods, so I will not bother with that. Okay. Now I'm getting this 395 Kelvin, which is, significantly above room temperature. It is actually above the boiling point of water. Assuming that the numbers reported by the spectroscopist is right. Okay. Now I'm just telling you, this is, though this is a very basic class, but if you look at the entire literature on hydrogen bonding, there's a huge disagreement, so to say, upon the, the delta H, the delta S, what are the contributors to delta H, how do these phase transitions occur, so on and so forth, right? But simply said, in this kind of a problem, you should get roughly, 395 Kelvin, okay? So, this is something I wanted to tell you, energetics of hydrogen bonds in peptides. So, they are not even talking of proteins, but rather peptides. For those of you who are interested, I have just put the, I have referred to the papers. This is a 2003 paper. Correct strength of such hydrogen bonds is experimentally known to vary greatly from 5 to 6 kcal per mole. Okay? So again, even though we are talking of a protein, an internal protein hydrogen bond, please keep quiet. Feel free to leave if you are not interested. I'm happy to. If you have thumbed yourself and you want to leave, you might. I don't have any problems. Okay. So we are talking of internal protein hydrogen bonds. Okay. So if you recall those movies, very broadly speaking, we are going to categorize two kinds of hydrogen bonds: water with water, water with a protein. Okay. And there's usually a competition. It's kind of a hand holding. You want to kind of, make these hydrogen bonds with the same species or with a protein, okay? So when you're talking of protein-protein hydrogen bonds, if you have it in vacuum, okay, you can actually do these gas phase experiments where you look at peptides in vacuum. There are plenty of people here in India as well who do these gas phase spectroscopy experiments, okay? There you have 5 to 6 kcal per mole for the isolated bond, and you see the protein-protein hydrogen bond becomes much weaker if I immerse it in water. Okay? It's about a tenth. Okay? It's almost by an order of magnitude. So this is a schematic diagram again taken from the same paper. If I am talking of the donor-acceptor distance, okay, how many of you remember the hydrogen bond and alpha helix and beta sheet? C double bond O NH, right? So, they are talking of, so one is the donor, one is the acceptor, okay? Nitrogen is the donor, the oxygen of the carbonyl is a typical acceptor. So, the donor-acceptor distance, if you look at the free energy of the hydrogen bond, you can actually get a plot of this kind. What do you notice in this plot? There's a minimum, okay? So, this is, the numbers are not given here, this is where it is very suitable. And the moment it is taken apart, this is typically your 2.8 to whatever, some 3-ish angstroms. If I take it further away, okay, then, it is that hydrogen bond is breaking and this value will correspond to the activation energy for hydrogen bond breaking. Okay, that is the amount of energy you need to break a certain kind of hydrogen bond, and this is assuming that your spectroscopist groups, they have been able to track this down very specifically. Okay, now, so just a few diagrams. Remember that this paper is old. Okay, this is near 30 plus years old now, right? 2003, 13, 23, no, 20 plus years old. So what happens when proteins are shifted from your gas phase to water? Okay, so alpha helix in vacuum or gas phase, we are going to say it similarly. You see, the moment you put it in water, the hydrogen bonds get a little bit less aligned. Okay, the internal hydrogen bonds. Same for alpha helix, same for beta sheets. You see, you can recognize these hydrogen bonds which are a little bit now misaligned. Why? Why are these misaligned? They want to hydrogen bond with the, so water is like a disruptor in this case. It is kind of breaking that internal stability. Okay, that is why, water is called the lubricant of life. Water is, your proteins will only function if you have water. Water helps to open up active sites in your enzymes. All these mechanisms, whatever biomolecular mechanisms you are talking about, okay, will happen in water because you need water to make sure that your proteins are dynamic enough. Okay, it's in a simple statement. Alright, so let's look at some more information. This is again a result of a computer simulation from that 2003 paper. And for those of you, at least people in my group, you will realize these are very short computer simulations. They have looked at the NHO distance of proteins, okay, protein NHO distance. You see that when you start it in water, this is backbone protein. Sorry, I'll clear this up. It is going down, right? So hydrogen bonds rupture, decrease in lifetimes. Water hydrogen bonds compete with internal protein hydrogen bonds, and there are some values. Okay. So when I am talking of an alpha helix, what is yes?
In the previous slide.
Yeah. They are going down is what you are saying, right?
No, actually,
Instead of going up. Is that what you are saying?
no, actually, we are seeing the NHO bond. Is this a particular bond or average of?
This is a hydrogen bond. We are talking of hydrogen. We are not talking of covalent bonds in today's lecture.
The hydrogen bond, I mean, that is single bond or
Say that again?
NHO bond, the hydrogen bond. Is a particular hydrogen bond?
No, this is a statistical average. They are looking at one, but you can do this for all the ones that are present. And you can, get distributions and statistics of it.
It represents all the bonds.
This one plot cannot represent all the bonds. They are just showing one sample. Okay, but this has to be done repeatedly before you can get your accurate statistics. But let's look at this number. So this is hydrogen bond activation energy for alpha helix and beta sheet in gas phase and water. So gas phase and vacuum they are using, that's a very standard thing in spectroscopy. If you go to any of the spectroscopy labs, sometimes they'll say vacuum, sometimes they'll say gas phase. Don't let that bother you much. Huh? What is the dielectric constant of air and of vacuum? They are very similar, right? So we won't get into that discussion. But you see, the activation energy for the proteins, either alpha helix or beta sheet in vacuum, is much higher than that in water. So when I'm, essentially what does this mean? If I'm immersing it in water, it's much easier for me to rupture an internal protein hydrogen bond, simply, okay? And the rate of breakage, how many am I breaking per unit time, is given by, this is the Arrhenius type thing. We have an A is given in per second. This is e to the power minus activation energy by R. Okay? You can check for yourself if these numbers are correct. You can verify these numbers. Now, so I would like people to quickly note down these alpha helix, beta sheet. You don't bother about the A. Just write down these 4 numbers because we are going to use it in the next problem. Alpha helix, beta sheet, EA, and these are kcal per mole, okay? Note down those numbers in your notebook. I see a lot of people are hesitant to write nowadays, huh? Type if you don't want to write, but note the information down, whatever works, okay? So we have the activation energies, alright? We are going to use this. Alright, so just we'll come back to that problem. Just a bit of a note here. Just make sure you have put those numbers down. I'm not going to bother you with the details, but just for the sake of completion, again I have put a reference there. Now you are absolutely, in your right to ask that, you're telling me that hydrogen bond is donor, acceptor, this geometry, that arrangement, but what causes a hydrogen bond? Okay, that rigorously speaking you should be asking a quantum chemist. But however, you see there's one electrostatic interaction and there are a bunch of many other kinds of interactions. Okay, dipole, secondary. So, there are different categories of looking at these interactions. But I'll just tell you some of the non-electrostatic components. So, there is an electrostatic component and most of it is non-electrostatic. So, if I just add those things, you will get a net hydrogen bond. So, in principle, I don't know, those of you who lean a little bit into chemistry and if you want to, do quantum chemistry, you can actually look at all the components of these. There are methods to do such calculations, so on and so forth. But I'm going to lump most of the non-electrostatic parts into something known as van der Waals interactions. This also sometime in chemistry they'll be taught. Van der Waals interactions are very important when you're talking of these, organic frameworks, many other kinds of things. And proteins, of course, they're very important. So these van der Waals interactions, they have a bit of a shape like this. What does this mean? This is the net, this is a typical van der Waals interaction. They are very stable, they have a minimum. Okay. Closer to that, they are repulsive. As you go away from that, two particles don't care for each other. If you are talking of only van der Waals. So, in your mind you can think of hydrogen bonds as some electrostatics and some van der Waals. It's an approximation, okay? I'm just going to call it, let's assume, EHB is approximately E electrostatic. I'm putting Q means electrostatic. I'm using the shorthand for charge. plus E van der Waals. Okay, now let's do something. Again, van der Waals are a major contributor. Why am I saying this? I have some justification, okay? You're free to read it. Now pay a little bit of close attention. It's not difficult, but you need to understand the thread of logic here. So, how many of you recognize the first equation? If you ignore that constant, no, now I will guys. Free energy of inserting some into water. Surface tension times area. 4 pi r square, we are just multiplied by surface tension. Where did ideal gas come from? We need to have a coffee counter right outside. So we'll make it mandatory. You know, have at least 1 cup of coffee and then come in. Goes for me too. Okay? Alright. So if I look at this, of course there's some kind of an intercept. Right? But the free energy of nonpolar hydration more or less scales with the area. For a perfect sphere, it will be 4 pi r square, but I have just argued to you that no biomolecule is a perfect sphere. Your DNA is never a perfect sphere, right? Think of any. Is your hemoglobin a perfect sphere? Any of the proteins that you know, none of them are exactly spherical, right? So all said and done, this has a linear relationship and a slope. Now let's say a model. Okay, by model we need I mean a physical model. I don't mean a model that a person model. I mean a physical model. Okay, a biophysical model assumes that only van der Waals forces contribute to protein water hydrogen bonding. Okay, protein water hydrogen bonding whatever. Sorry, you know that's right. No, solvated paper. So, what have they done? They have changed the free energy to delta U van der Waals. They have, they have some kind of, they have defined a surface tension due to van der Waals interaction. This one, okay, A is, one kind of, we call it the solvent accessible surface area, and B is some intercept, okay. They have given your surface tension due to van der Waals is minus 84 calories per mole per angstrom square. So it is some energy per mole times the surface area, right? And this number has been given. So how will your whoever has done this, if I want to plot, very simply said, what will this look like? Straight line, but the intercept giving your V with the slope giving your surface tension. At least, some kind of surface tension. Okay? I'm giving you, I don't know, along this class I've dropped several hints as to how, these research models are created, right? So, those of you who were listening carefully, I hope it will be useful. But even if it's not useful, it's okay. Now, so let's say we are looking at a protein whose SASA, we use this term very much, we call it SASA, it's solvent accessible surface area. Your inner part of the protein is actually not seeing water at all. If you have a protein, there's certain parts of the protein which will be accessible to water. The rest of it, unless you do something funny with the water, will never see water. Okay? Pretty much right after synthesis, it will not see any water at all. If a protein of SASA 6 nanometer square is submerged in water, estimate the energetic, I have set cost or favorability of doing this insertion. Is it favorable or costly? At room temperature, given this data. Will be how much? 6 nanometer square is 600 angstrom square, right? Please. By the way, what is going to be the units of my intercept? Calorie per mole. Okay? plus, tell me if I'm doing things right or wrong. Because we are trying to do kilocalorie, I should do this. Because this thing is given in, no, we should not be doing this, right? No, this is fine. This is fine. We should not be doing this part. We'll get our results in calorie per mole. How much is this? Something like minus 50, right? Units? Kcal per mole. Kcal? Because you are dealing with, so this is favorable if I only consider that, if my model says that, but then you have to obviously, you have to verify it either with a spectroscopic experiment or with a simulation. Now let us take it to another part. Tell me if I have made any unit error. It should be 50.4. Can the PS fit into this? It's fine, Kcal? Yeah. Okay. Again, guys, if you make a mistake in the units, I'm sorry, but we are going to. If I have a bunch of people who have done it correctly versus someone who has not, obviously, we cannot be the same to everybody. Yes, Abhinav. That is the energy associated. Okay? We are talking of the change in the energy.
Because delta G has changed to delta U, so there has to be some significance.
That is the free energy. Okay? That is the energy. Look. Do you understand the difference between energy and free energy? What is free energy? It is the maximum amount of work that you can extract, right? So in equilibrium, you should have the lowest free energy because you can't extract anything more from you. Derivative will be zero. Here, we are assuming that the energetic component. Now your energy can be internal energy, can be whatever, can be interaction energy, doesn't matter. Okay, but energy is distinct from free energy. This is the energetic change when I am immersing my protein of a surface area A into water.
So we are saying that all the
That is the change in energy of the whole system.
So we are saying all the free energy that we get is actually getting from van der Waals.
In this model, we are saying that van der Waals is the major contributor. I will conveniently neglect the rest. That's why I said this is a model. Okay. You can make any model that you want, but it has to stand true. A model is like a hypothesis which has to be tested. Testable. Yes. It's favorable for submersion. So when I take my protein, okay, I take my protein of a surface area, I dunk it in water. My energy for the whole system is coming down. Protein alone, water alone, I take it down. Going to these van der Waals interactions, it is going up. As per this one. Okay. Abhinav, you can come back to me and we can have other discussions or more discussions on energy and free energy. Or anybody can come. Alright, so that is part A. I kept now, assuming that EA, the activation, the protein water activation, we have put all these values here. I told you to, I told you to mark this and I told you to mark this. Assuming that activation energy protein water is the average distance of activation energy in vacuum and activation energy in water. Find the number of protein water hydrogen bonds that can be broken ignore entropic effects. There's a bit of, this is wordy, and I know that some of you, if you do this sincerely, you're in the okay regime. What am I saying? I'm saying that, I have activation energy. What is the activation energy? I told you a few slides back. It is the energy required to rupture, to break my protein. You can just imagine alpha helix if you wish. I'm going to break that hydrogen bond, either in vacuum or in water. To break it in vacuum, I need for an alpha helix 5.57 kcal per mole. To break it, if the whole thing is in water, I only need 1.93 kcal per mole. So the difference between them is the activation energy of protein water. That is protein in vacuum, protein in water. So if I simply take that, so what is 5.57 minus 1.93? 3.64. What is 4.79 minus 1.58? 3. So what is the average of 3.64 and 3.21? 3.4-ish. 3.425. So I'm simply telling you, if you read this carefully, I'm telling you that activation energy for a protein water hydrogen bond is, how much does it come to? 3.43 or something. Right? So how many hydrogen bonds can I break? Okay, that is just a moment. Okay, so I'm going to combine. So here we got 50.4 kcal per mole. Okay, and the activation energy of each is 2.43. So if I ignore entropic effects with my 50 point, I told you, right, this is like accounts. My negative 50.43, which is a favorable process, will allow me to break approximately how many hydrogen bonds. If I just say I don't care about rearrangement and entropy, break and all those things, it is going to break. I'm going to ignore entropy. How many? 15 to 16 is what the number will come to. Okay? So please understand this problem a little bit. Yeah? Right? 50.43. 50.43 divided by 3.4. Should be roughly, I know 3 15s are 45, I know 3 16s are 48, whatever. So it should be in that vicinity, na? Yeah, so you do, to get the average difference, if you want, I can put it like this. I can put it, if you wish, oops, I can put it this way. Okay? I got this from this guy, this guy, this guy, this guy. Okay? The protein water activation energy. Alright. So again, if you buy my argument that if I have this standalone protein in vacuum, okay, or in air, to disrupt, just imagine this as a helix. I'm just breaking one of those C double bond O RH helical hydrogen bond, right? It will cost me 5.57 kcal. That is my activation energy. Now I take it from vacuum, I put it in water, my cost goes down. I'm only paying 1.93. So I'm making an argument, okay, this is again a model. This is how the theoreticians work, or people who do modeling work, or even experimentalists work, This is making a hypothesis. I'm saying, instead of a protein and a protein water, protein hydrogen bond, internal protein hydrogen bond, if I have a protein making a hydrogen bond with water, a protein, one of your C double bond O making a hydrogen bond with water, what is its activation energy? I'm saying it is simply a difference of those two. Okay, protein in vacuum, protein in water, so protein water, I'm simply saying it is a difference in that. And I notice that alpha helix and beta sheet have different numbers. Okay. Because for a given protein, I don't know how much alpha helix is there, how much beta sheet is there. So I'll make a simplistic argument that the protein water activation energy is simply an average of those two, and that is what we have done. Got it? Now with that,
We can only have one. The average of 1.9 and 1.58. Something around 1.
no, so we did right. 5.57 minus 1.93 was some 3.74, and 4.79 minus 1.58 was 3.29.
3.29 is less than.
No, just average your 3.29, just average your alpha helix and your beta sheet.
So, okay, we get an average of
And you get roughly 3.425, which is 3.4. Got it? Strictly speaking, this is 3.425. Yeah, because what we have got is the total. What you got, oops, exactly, we got total minus 50. For each I am paying 3.43, I am giving a damn to any rearrangement. I am ignoring entropy. If that is my argument, I am able to break about 16-ish number of, I can afford to break, please listen to this statement carefully. I can afford to break about 16 hydrogen bonds. See, these are, you have to go back a little bit into history. There was a time when people did not appreciate entropic effects at all. Okay, back in the day, these arguments used to be made, but now as we are getting wiser by the day, we know that there's a cost. You cannot really ignore the rearrangement costs.
zone 16, assuming that there are equal number
I'm paying the same cost to all of it, equal number of, look, there can also be other kinds of helices, there can be turns. Yeah, maybe. Got it? Please get a grasp on this problem. This is a simple problem. The math is simple. And those of you who are confused about R, KB, temperature, scaling, 0.58, I'm telling you, please do not do a disservice to yourself by ignoring these conversions. You have it on the tip of your fingers. You can do it correctly. It's useful. So please go over all this, and I think today is the last formal lecture. Tomorrow, I don't know if it will be morning or evening. Acha, can we again shift to 6:30 p.m.? Is that okay? The gym guys? No, why? Biolab is what time? No, I'm talking tomorrow. Yeah?
The tutorial is getting switched.
What time?
What?
So, okay, let's stick to 6 p.m. Okay.